Good morning. Hi, everyone. Thank you so much for coming to the Open Day. It's so exciting to have you to be with us here today. Today, I'm going to give you a taster lectures about generative AIs in health informatics.
So I could hear me.
Actually, I can just shout. I think you can hear me pretty well. So, no. Okay. So, right. First broad definition about what health informatics is actually just involve the use of intelligence and intelligent use of information and technology for better care for patients, right? So broadly speaking, all we talk about is any sort of technology you come across and then apply that to healthcare settings. So sorry, I forgot to introduce myself. So my name is Tingting Zhu. I am a fellow of Keller College, and I'm also a stipendiary lecturer at Mansfield College, Oxford. So I'm also lectures engineering and mathematics in year 1 and year 2. If anyone has questions later on, please feel free to talk to me about it. Okay, so first thing about health informatics, that's what we just described. And I also teach the 4 years, which is the fourth year MEng course about C22. In particular, I teach the module Health Informatics. What does that mean is actually we're trying to expect students to understand the use of data science to tackle healthcare problems. So what is data science? You might have these questions, right? So actually data science composed of computer science, math and statistics, as well as domain knowledge. In this sense, domain knowledge is actually healthcare, right? So we're tackling healthcare problems. So if you apply computer science to healthcare, you are developing software tool to create decision support tool. If you apply math and statistical model to healthcare, you are now doing fundamental and translational research. And so machine learning is actually a mixture between computer science and math and statistics. So if you apply machine learning to health, you're doing data science, as this course implies. Okay, in these particular modules I teach, I also touch on electronic health records, which is something that we will touch on later on in this lecture. And I also look into how we understand sensor data. So sensor data means something that you wear for Fitbit or your Apple Watch. How to extract those information and analyze them. And also, I teach about clinical informatics. Clinical informatics means that we're trying to understand how clinicians and how doctors create risk scores to monitor health of an individual. And then we dive deeper into see how we create model to predict risk and monitoring health of the patients. So the first thing we talk about today is electronic health records. So here I'm just giving you exemplar things about what we do in health informatics, right? So, and then we later introduce why and how we use generative AI for health informatics in electronic health records. The first thing, I guess, for a lot of questions that people might have in mind, what is electronic health records, right? So health record essentially is nothing but encounter of you that you meet with clinicians, your GPs, your hospital visit. So it's all a journey of you in health, right? It captures all the information in you. And most of us have patient paper records. So we have a pile of information that we collect together. Why there's a need for electronic versions? So this is a picture that I want to show you. Imagine you are standing in front of a storage room where you collect a paper, like all the paper of all the patient records. The first thing you feel is that, do we have storage for all of them? The answer probably no. And also paper records is problematic is that you might lose the information. It's hard to find and it's hard to track, right? And most importantly, we can't share. So imagine if I'm reading someone else's patient record in paper, you're going to have to wait in the queue. You're going to wait until someone else to give you the access to it. So that's why we want to have electronic version of it. And this is a pictures I'm just trying to show you here what an electronic health record system looks like. So it's quite got a lot of information. As you can see that, the mouse, that's interesting. Never mind. So highlight for real. But anyway, so all you're trying to essentially capture is that you got all your background information, your date of birth, your medical history, and then also the reason why you admit to hospital in this case. Most importantly, it does capture, as I highlighted here, the vital signs of your informations. What do I mean by vital signs? Your blood pressure, your heart rate, your breathing rate, and your temperature. So these are what we call the vital signals that we capture. We also capture the blood pressure, the blood test results that you might get when being collected, and also the medications you have and the procedure you've been taking. So with all of this rich information we have in EHR, what can we do with it? What's the benefit of it? So imagine what I just previously described, that you collect all of this information inside you and you get them change over time, right? It's a trajectory. I'm following your health change over time. That actually allow us to phenotype you. What does phenotype mean? Phenotype essentially means that we are grouping or clustering you into subgroups of risk. What that means is that now we can tell putting you at different risk category. So imagine you are diabetic. Most of you will probably hear that you're type 1 or type 2 diabetes, right? So this is what we're essentially doing. We're grouping you into subgroups, allows us to ask the what if questions. The what if question is, can we actually now tell your disease progression if you're unwell? Can we actually respond to your personal treatment? If something happened to you, what treatment is useful? And also, most importantly, if we track your health, can we tell any abnormality, something that is outside the ordinary, right? So this is so exciting, but there are challenges in HR. First and foremost, you've seen that pictures before, isn't system. It's electronic system, it's costly. It's a lot of money involved to actually operate, right? So, and also, because now we're storing everything on the cloud, you might ask, what happens if we got a power cut? Do we need to have backup, right? And secondly, is that we have a lot of patient information now stored and electronically, and if we want to create models to understand disease, we probably need consent. We need patient to consent retrospectively. So a lot of time that patients are lost to follow up, meaning that we can't track them anymore. And also, most importantly, if the electronic system have restrict access because patient privacy. So imagine if I'm a clinician in charge of you, I cannot stay poking other people's record for fun. I can only look at yours, right? So that is something that people need to be aware of. It's not because I got access to everyone, I can then start poking everyone else. So you got restrict access, and also different hospital or different trust in the UK here, we don't actually share the same EHR system. So the interoperative problem is difficult. And not to mention, we have standards across different countries. How can we share if we are different countries, right? And most importantly, security issues. So because it's electronic-wise, a lot of time we talked about how secure is our data store. There's a recent event, I don't know if some of you come across, last June, there's one hospital in London was actually had a ransomware attack. So any of you not familiar with ransomware attack, it essentially means that the attacker get access to the patient record illegally, it held the information by locking it, and then come back to you and ask you for a ransom so they can give you back the access. That's what it does, right? So they're not going to steal it and sell it. They couldn't. So they're trying to come back and sell, get money out of it, which is amazing. So this is something that actually hinders us to use this rich information. So with all of these challenges, what if we can synthesize patient data? If we can generate patient data without needing actually touching the real patient data, but making sure that the data that we synthesize is as real as possible. So that is where generative AI come to play. So don't worry for concept-wise, if you don't understand generative AI, I'm going to walk you through within a minute, you will understand. So starting from the top, artificial intelligence. So it's just essentially a computer program, a machine that can adapt and sense like human being. And machine learning, on the other hand, as the name implies, machine learning. So we're trying to teach the machine, the AI, to learn patterns, right? So we're teaching the machine to learn patterns, and deep learning is just a subset of machine learning where it utilizes neural networks. Neural network is just mimicking what we do in neurons in our brain, that how we connect, formulate a network. So that's why we call neural network, right? And the generative AI is a further subset of deep learning that essentially is a suite of machine learning models that what we use to create content. So we train the model and we can create contents in this application like EHR data. Okay, having generative AI, that's really beneficial. Why? Think about what we can do more of it. So for some of you might come across the concept of digital twin. So a digitized version of our online. So if we are able to generate data, we can now create a digitized version of me online. That allows us the questions that, if I got my blood pressures missing, I can actually impute it based on my heart rate, right? Internal phenotyping, I just mentioned, and risk prediction, now we can use generative AI to help us to do so if we are able to create the digital twin version of us. And most importantly, allow us to do more personalized treatment recommendation. Is treatment A over B, or at what doses is particularly useful for me as myself? Okay, so just to, sorry.
You're right.
Yeah. Okay, so today in this lecture is going to learn about one type of generative AI called the GAN, Generative Adversarial Network. I'm going to give you a story about how the counterfeiter make money and how the bank clerk is going to try to discriminate what is real and what is fake. And that is all GAN is about. So starting with, you got some random paper. So the counterfeiter gets some random paper look like they're money papers. If the counterfeiter, we'll call it a generator network, is going to generate, making fake money. And then what happened is that then the counterfeiter will pass the money on to the bank clerk. The bank clerk actually have access to the real currency. And if we're trying to examine, so we call it the discriminator, whether that fake money is real or not, right? So what it is that the bank clerk would then make a decision and say, would I accept or reject this fake version of money? When it comes to rejection, and then it goes back to the counterfeiter saying like, wow, I probably need to make a better version of this fake money because it's rejected, right? So then it just iterates throughout the whole process until the bank clerk can no longer tell the difference between the fake and the real. And this all essentially what this GAN model, a generative model AI, is about. So if we take this concept and apply it to a mathematical formulation, so essentially what we have is random noise sets, and then we got a generator out of our dear counterfeiter that generates some fake money, and then we have our input X, which are the real currency, and then we got our bank clerk D, which is the discriminator, that's going to give you an estimate of probability whether the GZ is the same as X. So with a probability of P, with a rejection of 1 minus P. Yeah? Okay, so essentially, the discriminator and the generators are playing games. They are playing sort of what we call the min-max game with a particular value function. So this is the function it is, but don't worry, let's take a step back and let's digest it slowly. So we got the GZ, which is the generator that outputs the money as essentially giving some random noise. And then you got the discriminator. So discriminator have two components. The first part is the discriminator able to estimate the probability of a real money that is essentially real. And also the DGZ, in this case, on this side here, is the discriminant estimation of the probability that a fake sample is now being treated real. So, and then the other part here, for the EX and EZ, essentially just on average, the expectation over all the sample, what will be your average estimation? That's all. And so when I just keep saying min-max game, right? Why is it minimum and maximum in this sense? What are we doing here? So maximum, meaning that we want to maximize how well the bank clerk is. We've got to train the bank clerk to be excellent in telling you what is real, what is fake, right? So we need to make sure we train the discriminator really well. So we want to maximize how well we estimate a real money and indeed is real. And then we want to, what else is that? We want to minimize how much of an error mistake that the generator, which is the counterfactor make. Meaning that because if he can make we want to make sure the generator, because the generator cannot actually affect the discriminator. So the counterfeiter cannot change the view of the bank clerk, right? So what it can do, what we can essentially do is that we basically want to train the generator as good as well as it is, in this case, minimizing 1 minus the generator discriminative probability or capability to estimate the difference. So that's why it's a min-max gain. Essentially is that we want to train the generator to generate really realistic money, and we want to make sure that the discriminator are also competent in telling the difference. So we do this game in training, an alternate process, and then it will stop until the discriminator, which the bank clerk cannot tell the difference between fake and real money. And that's all. It's GANs. Right? So just recap, what we essentially want to do is that we got some real patient information, it's right on top here, and then we want to essentially generate something that is as close as to real, but yet synthetic. They're not real patient information because we need to be sure that there's patient privacy, and we don't want to, it's too risky to transfer real patient information across, right? So we can synthesize the patient data. So my group and I actually done some work on GANs, and here I want to share some results that we've done so far. So we can't compare like with like in the sense that what is the real patient value versus what's synthetic, because at the end of the day, we're not generating like with like. That's really important because we don't want to learn like with like. We don't want to make a copy of the same exact patient, but we just want to make sure that we're creating something is as realistic, share all the characteristics, but not real. Yeah? So, okay, so here just showing you a correlation values. So on the left column, you got real data, the correlation among different variables. And on the right side, that is the synthetic data. So we are comparing the correlation between them, and we can get as good as above 80%. And but the least thing that we want to do is actually not just look at correlation. We want to create a decision support tool, right? So what does that mean? That we want to use the synthetic data to train a model, as I mentioned just now about machine learning, which is teaching the machine, teaching the program to learn. And so in a way, instead of using real patient data, we can now use synthetic data. So here showcasing that we have what we're doing is treatment intervention. So we have an observation window of 12 hours, and then we want to make a prediction. And then we use one of kind of machine learning model, in this case here, let's call it LSTM, right? It's just a long short-term memory, a classifier, it's just a machine learning model. That's not the key of this content here. We just say we use any sort of machine learning model, and then now we want to do task predictions. We want to predict what happened in the next 12 hours of the full outcome of intervention. So if someone is having an intervention on, it can be 2 outcomes. So it can remain on and it can remain off. If somebody off, and then they can turn on and off of having such an intervention. So what we did is, instead of training the observation window with real patient, we just synthesize it completely. And we just synthesize the data, and then we're going to use that to train the model. And here just showing you results that we're testing on some data set, that you see that here on the left side, we train on real and test on real. What does that mean? So we're taking out real patient sample, we trained it, and then we're testing on another subset of real patient sample. And this is the results that we get for different sort of treatment. And you can see that this is like our gold standard, as if we see real patient data. And then what we did is we train on completely synthesized patient data, not real at all. And then we want to see how far can we get. And then we test on the same exact real patient group. And then you can see that the Verisal model actually showcasing that way, as we are getting as close as if we're seeing the real data for training. So this is what we're trying to achieve with generative AI. Okay, so far we just touched on a bit of electronic health records. The broad spectrum of medical data is much more. You have, electrocardiogram, for example, which is electrophysiology that monitor the activity of heart. You got EEG that monitor the brain wave. You got eye tracking, you also have different sort of modality as well. And there's amount of text that you could have and mine through medical data. And the last but not least is, I haven't touched on, is medical imaging. So you've got different kind of images that you have. So that's what we call the multimodality data, right? Some of you might come across the hype about generative AI when they talk about ChatGPT, they talk about Gemini. Generally speaking, we talk about large language model, right? You say, well, why can't we just use those models to generate those information? It seems as possible and possible. It's actually quite tricky with medical data. Here I'm showing you two examples. That on the left side, basically, I have prompt, basically type in some test guide and say, can you generate electronic health record for me, right? All you get is generally a cartoon-looking pictures, first of all, and then with some background information as it may imply that has to do with medical information. And as you can see that the content actually is not very readable in most of the things. So it's still quite far away. So then the next one, what I did was, I prompted a bit more. I give them my expert guidance. I say, well, now I want a patient sitting in bed. I want a bedside monitoring device showing vital sign. I even gave an image of a real image to help it to create it, right? So it's doing really good in creating real patient data. As you can see, we do believe that might be a real patient, isn't it? But if you look closely on the monitor device, you will see it's just not essentially creating realistic granular information. So it's quite far away, as we say, is that to meet the reality when it comes to medical care. And so today I'd like to sort of conclude my talk by talking about future challenges, in particular dealing with multimodal data. So we touch on about missing data, so data is missing, and also alignment issues that we haven't discussed. Imagine you take an ultrasound scan or an CT or X-ray. That is not synchronized with the data or the vital signs that you collect. So how do you align different modality of information? That's one of the challenge. And also, how do you fuse different kind of information where you got different modality here? And as you know, if we've got so many information, how do we process it? So that's a complexity in computation as well. So we just touched on how volume, variety, and also at velocity, as well as different sampling rates. So you have this sort of complexity in different dimensions when dealing with multimodal data. And the last but not least is decision-making complexity. So previously, we might not have all of this information in hands, but now we do. Would that actually change how we proceed, or how we, whether that is going to revolutionize how we actually deal with medical data, or whether that would change our decision in making for diagnosis for the future? Okay, thanks a lot for your time. That's it.